Okay, at the end of the last video, we had gotten ourselves to our first derivative that looked like this. All right, to find any local maxima or minima, we have to set this equal to 0. Well, note, a cannot be 0, because that says it. E to the bx will never be 0. That's a characteristic of exponential growth functions. So the only thing that could be set equal to 0 is this part of the derivative. So it turns out, I'll move that over, I divide by b. Now it's okay for me to divide by b because b can never be 0. So the x component will be 1 over b. All right, so there's the x coordinate of the local critical point, right? Now let's see what the next page says. Minima, and then find the points of inflection. We only have one, whoops, I'm sorry. There we go. We are only finding one critical point, 1. So I guess I need to figure out if this is a maxima or a minima, right? So I'm going to, if you look at the original function, we're trying to find out if this critical point is a maximum or a minimum. So if we look at this original function, y equals ax over e to the bx, note, a is positive here, right? A is greater than 0. E to the bx is always positive. So as x approaches infinity, as x gets really, really, really large, what happens is that this function approaches 0. Because the denominator, the exponential growth function, is approaching infinity much, much faster than the denominator's approaching infinity. So if the the denominator's growing bigger, it's going to be substantially larger than this, and so a number over a much, 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 much larger number is going to approach 0. So this function, which is positive, right? It's positive and is approaching 0 as x goes to infinity. That means this must be a maximum because we're positive, but we're heading towards 0. So this is a maximum point, a maxima, as they like to say. Okay? So if we look at the next page, what we're going to find is there are no minima, and now we want to find any points of inflection. So here we need to take that first derivative and get ourselves a second derivative. So what I did was I rewrote it to look like this. I just multiplied through. Oh, I'm just looking at it. I had it written here as y prime equals a 1 minus bx over e to the bx. So I just multiplied through the a. And now we're going to use this to find the second derivative. All right, I'm going to use the quotient rule, right? The quotient rule says f prime g minus fg prime over g squared. All right, so the derivative of the top, this is a constant, right? So the derivative is going to be negative ab, because that x goes away, times e to the bx. Let's see if I get rid of this for a second so I can write on here. Minus the top times the derivative of the bottom, which is e to the bx times b, right? All over e to the bx squared. So let's do some work. Notice this is a bx e to the bx. I'm going to distribute here. Minus ab e to the bx, right? That's the distribute across here, and then here I'm going to have minus, a minus means plus a b squared x e to the bx. So far so good, right? So what I can do is factor out the e to the bx. E to the bx, and that leaves negative ab, right? So pull that out. Minus ab, pull that out, plus ab squared x, right? Over ebx times ebx, e to the bx, whoops, because I just want to be able to do that. So my final y second derivative, if I collect like terms on top, is minus 2ab plus ab squared x over e to the bx. All right, if we want inflection points, right, we set the second derivative equal to 0. Oh, I believe I can factor something out here. Let's look. I will factor out an AB up here in that numerator. And because if I factor that out over here, I'm going to have a bx left. And if I factor out over here, I'm going to have a negative 2. So I'm going to turn this around and say it's now bx minus 2 on top, e to the bx on the bottom. All right. Well, due to the givens, a and b were both greater than 0. So these were both positive. This is positive. It's a growth function, exponential growth function. So the only thing we can set equal to 0 for x is this part of it right here. Bx minus 2 equals 0. Bx equals 2. X equals 2 over b. So x equals 2 over b is the x coordinates of our point of inflection. There's a lot to go through. We had to find some complicated derivatives, but we were able to do it. We had to use some thought too. If I go back to this page here, when we needed to decide if this was a maximum, I don't know if I went too far back, or a minimum, what we found was this original function, again, which was ax over e to the bx, right? As x went to infinity, the function approached 0, positive, positive, and if we look at, you know, an x of 1, an x of 2, an x of 3, this is all positive here, right? Positive, and it's heading towards 0, so it had to be a maximum. All right, let's move on. Here they're having us do some crazy derivatives again. All right, so let's look at this. So our original function, if I write here, L 1 plus AE to the minus KT. L, A, and K are positive constants. So what I can do is when I take the derivative, I'm going to bring out the L before I take the derivative of this mess that's left. Okay? So now y prime equals L. Let's take the derivative. Quotient rule. F prime g minus f g prime over g squared. Well, the derivative of the top is 0, isn't it? So that first term right here is going to be 0. Say minus the top, which is 1, right, times the derivative of the bottom. So the derivative of 1 is 0, plus, I think I missed the e there, didn't I? If I rewrite that, it looks like this. A e to the minus kt, right? So a e to the minus kt times the derivative of the exponent, which is what? Minus k. All of this over 1 plus a e to the minus kt squared. All right. Okay, so here's what we got. The first derivative, I have a negative here and here. This is going to be a positive. So I have this L. It's going to be positive now. I have an A and a K. So L times A times K, E to the minus KT over 1 plus A. And instead of writing it to the minus KT, I'm going to write it like this. A E over E to the KT. I can do that, right? And I'm also going to take this thing and move it in the denominator, because I can do that, right? Negative exponent moves it in the denominator. Whoops. E to the KT. So this is what I have. Now, I'm going to take this parentheses. I'm going to put it over a common denominator. It's E to the KT plus A over E to the KT. Okay, I'm just looking at that. And can't we, based on our exponent rules, write this as E to the KT plus A squared over E to the KT squared, right? Because 1/3 squared is the same as 1 squared over 3 squared. So I can certainly do what I just did here. So this becomes y prime equals LAK, that's what we have on top, right? E to the KT times E to the KT plus A squared over E to the KT squared. Now, looking just at our denominator, this takes out one of those, doesn't it? And if I say, instead of dividing by a fraction, I multiply by the reciprocal, this becomes LAK E to the KT over E to the KT plus A squared. This is my first derivative. Pretty crazy, huh? But it works. All right. I really have to get to the second derivative, so I'm going to come way back here and find us an empty slot. So if my first derivative was y equals KAL e to the KT over e KT plus A squared. All right, now let's go find the second derivative. Here we go. Again, I will use the quotient rule, right? The derivative of the top, constant, 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 right? K, A, L are constants. E to the KT, the derivative of this, which is just K, times the bottom, E, KT plus A squared, minus the top, KAL, E to the KT, times the derivative of the bottom, which is 2, EKT plus A, times the derivative of that inside, gosh darn it all, is E to the KT times K. Well, there's a lot going on here, okay? Lot. Right now, I'm just looking at the numerator. See if I can put some stuff together. There is... E the KT. This is inside the parentheses. This is inside the parentheses. I'm going to pull out an E to the KT. That's here and here, the ones that are not inside the parentheses. I can pull out one of the parentheses, EKT plus A, because that takes this and it gets rid of that one, doesn't it? I also have KALK. and Calk. So I have k squared